All right. Good morning, everyone. Now, so today we're going to look at something called tension. So, in our catalog of forces, we are finally down to one of the last few. So, but this is going to be one of the more confusing one. So, tension is a force along a rope, along some type of a thin, skinny, line-like material, like a rope or like a wire, the force along that. So, for example, you can have like, let's say, two people. Let's say they're participating in a game of tug of war. So there could be like a rope between the two of them, and they're pulling it toward their respective direction. So now within this rope, right, there will be a tension force. Pointing depends on who you ask. For example, if you ask the person on the left hand side right here, he's going to say, well, there's a force on the wire pulling me to the right hand side. Well, that's true, because that's from the person who's on the right hand side, right? So we call that tension, T or F of T. Okay, so same thing. So tension, T or, like FT, like that. So same name. Now, but if you ask the person who is on the right hand side about like, what do you feel now? She's going to say, hey, I feel like there's a force pulling me to the left from the wire or from the rope. And she will also be right. Okay, so there is a tension pulling that to the other side. Now, they are both right in their own perspectives. That's why when we talk about tension, we have to talk about who is talking. So this is the force that we call tension. Okay, so this is called the tension force. Tension force is along a rope or wire with no part of it perpendicular. So it's always along the wire. Now, and these two tension are the same. I mean, technically, I can erase all of these and just say tension. So it's a lot like gravity or the spring force. There are actually two of them, and they're exactly the same value. It just depends on who you're asking for. So the force on each of them is exactly the same. Now, what is tension though? Well, remember, we said everything is kind of just like, except for gravity, of course, electrostatic force in the sky. So what is the force of tension? What is it? So when you have a material like a rope or wire, okay, I know it doesn't seems like you can actually stretch it, but you could stretch like a wire or rope a little bit, right? If you pull it with hard enough force. So what are you actually stretching? When you're actually stretching the rope by a little bit, then it's almost like what we learned yesterday on elastic force, right? The rope would just like to get back to its original length, so therefore providing you with kind of like an elastic force. But in here, we call that tension. Now, you should be able to see from this screen right now. So the tension on the rope, right, for example, in a microscopic level, is actually just the forces in the molecular bonds. Now, remember, if you study chemistry or maybe from Science 10, you know that any object is held together by its molecule, which is, hold together with other molecule next to it by either covalent bond or ionic bond, right? Which means they're sharing electrons, or because one is positive, one is negative, so they're attracted to each other. So these covalent bond or ionic bonds acts like a tiny spring in between each molecule. They actually are like, they're not physically a spring. I know the picture make it look like it's a spring right now. If you look at like these pictures, these points right there. So the molecules or the little little circle, blue circle, and then the little spring in between is just, the ionic or covalent bond of electron sharing. Now, they want to share those electrons. So if you have to pull them apart, the molecule will not give up without a fight. So these tiny little spring-like force in between the molecule is what is keeping the rope together as a rope. So if you want to disturb it by stretching it, then what happened? Those little molecular bond is going to pull you back, just like a spring. That's actually a reason why physicists enjoy talking about springs, because the spring force or elastic force is also going to be able to explain where tensions come from. And even though they're not physical spring inside the molecule, but the calculations of that is almost exactly the same as if there was physical spring in between those atoms, which is pretty funny. Okay, now let's go back to the note. So the tension is just trying to get this wire or the rope back to its normal length. So in this picture, the tension will look like that. But what about, so for example, another example, what if I'm hanging something, on the ceiling? Let's say I'm hanging like a box on the ceiling. Then, what would the force look like? Well, in this case, it depends on who you ask. If you're asking the box, there's a tension pointing upward. If you're asking the ceiling, there's tension pointing downward. Okay, so that's how you look at it. Now, tension. Okay, so that's the write down. Tension occurs within a material when the material is being pulled or stretched. Okay, when a material is being pulled or stretched, then you have tension. Now, tension is an internal force. A ionic bond, covalent bond is the molecular bonding forces that acts like a spring that try to return, like maintain the structure of the object. And when you disturb it, it tries to go back into the structure. That's why it gives you tension. So it's an internal force that acts at all parts of the material, and it's along the direction of the rope or string or string or wire. And they act in both directions depending on which way you're looking from. Now, usually we only look at it from one way at a time. We try to make sure that one object is not moving at a time, but of course the force acts in both directions. Now, here we go. Okay, so then the questions start to be, once we learn about tension, the amount of question that we can do, the amount of level of difficulty of question that we can do, jump up drastically, because now we can have more than one object in a free body diagram. And when you have more than one object in a free body diagram, so you look at this first one, two car tied together by a rope with a person pulling it, or like jump ahead a little bit. What is this? This is a pulley. Okay. So a pulley system where the pulley can either go this way or that way, depending on which mass is heavier. It can spin around, so it's like a spinning wheel on top. So a pulley system, or if you look at next page, another pulley system, and this one is even more advanced, is a table with an object on top and a pulley in here with another hanging object on the side. Okay, so now we are going to get to that level eventually, but let's start simple. Let's start with just two objects on the ground being pulled by something. So considering two cars attached by a rope being pulled along a flat surface. Okay, so if mass 1, which is the one on the right hand side, is pulled to the right by a force of 40 Newton. Okay, so now what is in this picture is another person pulling the system to the right hand side. Okay, so it's trying to pull the system to the right hand side with a applied force. Okay, so now let's draw a applied force. Now, so the applied force, all right, so draw right here, right there, so there is an applied force. Okay, so now this applied force is 40 Newton. Okay, so like that, 40 Newton. And what else is here? Okay, let's draw a free body diagram for everyone in here. Everyone gets the free body diagram treatment. Okay, so force of gravity. Now we have two different objects, masses in this system, linked together by a wire in between. So we can no longer just use the word Fg, because then when you write it down on a piece of paper somewhere else, not directly below the picture, you do have no idea which Fg you're talking about. And they're different, right? One is 4 kilogram, one is 6 kilogram. So you have to name them. Fg1, Fg2, like this, because it's called mass 1, mass 2, right? Then we also have normal force, because why? On the ground. We're on the ground and the car is not flying. The car is not submerging underwater nor flying in the air. So there must be normal force for each of them that happens to balance exactly what the gravity is. Now, and that would also be labeled Fn1 and Fn2. Why? Because if you just put Fn, again, no one knows which one you're talking about. Okay, so there's a rope in between. A rope will have tension, so therefore we have tension. Depending on who you ask, the tension is either pointing to the left or pointing to the right, but we call it tension. Okay, so force of tension right there. Now, what else? Does the question mention anything about friction? Friction is neglectable. Okay, so let's assume that for this first example, there is no friction. Then we have this picture. Now, this picture at this point is done. Okay, so today, the most important lesson, I could actually say, other than Newton's 3 laws of motion, the most important technique you're going to learn today right now. So we're going to learn how to write a F-net equation, which we already know how to write it for a single object, but how to write a F-net system equation. Okay, so what's the difference? So how do you write an F-net, net force, system equation? Now, when do we have to use this method? When we have more than one object linked together by a wire. Okay, you will get this kind of question. This kind of question is actually named after a scientist, Edward. So it's called Edward's machine. So these type of question, when you have more than one object linked together by a pulley, and sometimes not by a pulley, but more than one object linked together with a wire or string, it's called Edward's machine. Okay, and whenever you see an Edward's machine question, you have to use this method, which is called system net force. Now, how do you consider system net force? So what you need to do, step 1, is to realize that you are dealing with this kind of problem. Step 2, finish your free body diagram on the object, including the tensions. Step 3, see who's left. Now, what does that mean? This is the most important step. You have to be able to look at this picture and tell me who did not die. Most forces are cancelled out. All committed suicide for some reason. There's usually only a few things left. Now, we look at this picture and let's do crossing out the forces that are dead, right? So, for example, Fn2, Fg is gone. Why? Because they have to be opposite and pointing to away from each other, and they have the same value. Otherwise, the car is going to fly, which is not going to happen. So they pass out. Okay, so they're both gone. We pass them. Fn1 and Fg1 is also gone. One is pointing up, one is pointing down, same amount, right? Now, can you see the two tension in the middle? Tension is an internal force. That means if you look at the entire picture as one single object, tension is always internally cancelling out each other. That means, yes, tension might be 100 Newton to the left or to the right. I don't care. If it's 100 Newton to the left on this guy, then it's 100 Newton to the right on the other guy. So they cancel out, right? They're completely opposite direction with exactly the same value. So that cancels out. Now, once everything in here is cancelled out like that, what is the only force left? You can see that, right? A pi force. This is the only force left. Nothing else is pointing to the left-hand side. No one is fighting him. Therefore, that one force right there is whatever remains, which is now crowned the name net force of the system. So the net force of the system is the only force remaining, or maybe sometimes there are more than one, are the only forces remaining, okay? And that is the net force of the system. So we look at the entire system as one single thing. So in this example, the net force remaining is Fa. Now, in every different question, the F net of the system could be different things. For example, in some question, it could be the pi force. Some question, it could be the pi force minus the friction if there are frictions on the ground. Sometimes the F net of the system is just the friction if a car is trying to slow down. There are many, many, many different combinations. But what doesn't change is the fact that F net, well, what is F net equal to? Newton's second law, ladies and gentlemen. F net always equal to ma, right? So what does F net of the system equal to? Well, F net of the system equals ma, except it's the mass of the system instead of just the mass of one object. Okay? The mass of the system. So F net equals to ma. So regular F flat equal to small ma, one object, right? System F flat equal to system ma, the mass of the entire system. Now, the applied force, of course, we can substitute right here already, is 40 Newton. What is the mass of the system? Well, this system has two objects, a 6 kilogram object and a 4 kilogram object. So together, 10 kilogram in total, right? So that's exactly what we're going to put in. So we have a 6 kilogram object plus a 4 kilogram object multiplied by an acceleration is equal to 40. So what do? Add the 4 and 6 together, and then which is 10, divide both sides by 10, the acceleration is done. So acceleration is now done. Now, but what is this acceleration? So that's 4 meters per second square going to the right hand side. There you go. Okay. So, but what is this acceleration? Well, is this acceleration from car 1 or car 2? What will your answer be? Well, you might say, Mr. Chang, they're linked together. Yes, they are. So what does that mean? That means they have to move and stop together. Because these two objects are physically linked together, they would have to have the same acceleration. So this value right here is the acceleration for car 1, but it's also the acceleration for car 2. So it doesn't matter which one the question asks you to do, you are getting that number. Don't try to get just car 1 or car 2. This number is for car 1 and car 2. So that's why in your direction, usually you have to say right hand side for which car? You say right hand side for car 1. Now, you might say, Mr. Chang, wait, why do I have to say that? Both are going to the right. Yes, in this question, both are going to the right. Later on the next page, one object goes this way, the other object goes up. You agree, right? Because the 6 kilogram box is heavier. Then you cannot just get me an acceleration and tell me that it goes up. Because are you saying that both of the box goes up? I don't agree. Only one of the box goes up. So you have to, after mentioning the direction from the acceleration, you have to tell me which box you're referring to. Now, there is no right or wrong answer. You can use either one of the boxes. You just have to, make sure you have the arrow correctly so that you can call it out the right way. Now, we finished this question. We got the acceleration. It looks very easy. And then you say, Mr. Chang, you said this chapter is hard. Oh, just wait for it. The acceleration is just the first step. The topic of today's lesson is called tension. And we just kill off tension while we're doing this. I mean, there's no way that we're killing off the only thing that we're trying to find in here, right? So what if the question actually asks you for tension? Okay? So now, when we are looking at the system net force equation, the tension always, okay, let me write down, always cancel out in the, let me write down very carefully, system net force equation. Okay, so the tension always cancels out in the system net force equation. Therefore, we cannot rely on this system net force equation to find tension because tension is already dead. Okay, so how can we find tension? Because we cannot use the system, why don't we use the individual object? So this is how you get tension. So that's another new thing you need to learn. Okay, so to get tension, you need to focus on one object. So to get tension, focus on one object. Now, because both car 1 and car 2 are tied together and they're both touching that tension, you can use either one of them. But one is better than the other. Why? Because if you look at the object 2 has 3 forces on it. Fn2, Fg2 tension. Now look at object 1. Object 1 has 4 forces on it. Fn1, Fg1 tension applied force. So if I'm focusing on one object, wouldn't it be better to focus on the one that has the one less force on it, right? Wouldn't that be nice? Okay, so we're going to focus on M2. Now, but it doesn't really matter if you use N1 though. Your equation will be one step longer and that's it. Okay, so focus on one object. Now, in this case, we pick object 1. So here's what you need to do. Pay very close attention. and take notes. First, draw the object again. Then complete its free body diagram with all the forces on the picture. Basically, just copy the free body diagram. Okay? Now, don't do anything unnecessary. This is object mass 2. Just write it down on the outside, and that's it. Ladies and gentlemen, look at this picture. And now, write down a net force equation. But this net force equation is only, okay, only for mass 2. Okay, so write down a regular, only for one mass, net force equation. Now I look at this picture, I see two things immediately. Number one, Fn2 and Fg2 is gone. Number two, the only thing left is tension. And no one is fighting that tension on the other side. So this is the winner. Okay? Now, also, how do you know tension is the winner? Look at the direction of your acceleration. To the right hand side, right? So your acceleration is going to the right hand side, including this box. So this box has an acceleration that points to the right hand side. So the winning force must be the one that points to the right hand side, which in this case is the tension. So once we establish the fact that tension wins, then we can write down the net force. Net force should be the winning force minus the losing force. But I look at the other side of this picture. Since there's no friction, there is no losing force on the other side. So that's it. The tension, the F net for the box 2 alone or car 2 alone is just tension. But remember what F net equals to. F net always equal to Newton's second law, ma. So now I can write ma equal to tension. Notice in here that this is a small m, and the last question wasn't big M, because that was an entire system, and this is only mass 2. Only mass 2 goes in there, which is 6 kilogram. Acceleration, oh wait a second, we did have acceleration. That's 4 meters per second squared from part A. So what does that tell you? In order to find friction, you have to first find acceleration. So if I ask you, if Mr. Chang is being mean, and I give you a question that asks you for the tension in between the two cars directly, that is asking you to find acceleration first, without really asking you. Because without acceleration, this will not be possible. So tensions require acceleration to be done first. Write it down. Okay, so now you're done. Well, I mean, multiply and then you're done. Tension, 24 Newton. Now, we don't have to put directions for tension. Because, okay, look at that picture. I can say right-hand side or left-hand side, depending on which car you ask, right? So just show me the picture, then I will know which way the tension is. You don't have to say right or left. Because it's both right or left, right and left. I mean, so you're saying like every single direction then. What's the point? Just show me in the picture. So this is a complete question. A lot of time, this is what you need to do. Get the acceleration and get the tension. Two things. Okay, so now let's summarize it. Since the tensions will cancel in the net force equation, right? So when you try to get tension, you only focus on one object. Now it doesn't matter which object, but since tension acts on both masses equally, we can use either object. Okay? All right. Now, and then we're going to jump to the next level. I will consider the question that we just did level 0. I'll now give you level 1. Okay, so in this pulley system, the rope is attached to a rollable pulley. So the pulley can rotate left, rotate right, and we have the objects over there. Now, if you want to draw the free body diagram, I would say there are tensions. Well, okay, now this is a little bit weird. So the tension is actually both pointing up. Because think about it, like mass 1 is going to think, oh, someone is pulling me up. And mass 2 is also going to think someone is pulling me up because of that pulley in the middle, right? So they're both going to think that there is the tension. Now, these two tensions are exactly the same. One wire, one tension. If you want two different tension in the same question, you'll have two different wire. So for example, right? If you have two boxes attached to a rope, like this, and then they are again attached to another rope, like so, like from a pulley, and like this. Now then, there will be two different tensions depending on what you're focusing on. So for example, this will be tension A, shared between the two boxes, and then you'll have like tension B, which is on this wire. So there will be tension A and tension B. Okay, so these two tensions are the same from the same wire, right? And these two tensions in the bottoms are the same because they're from the same wire. Okay, one wire, there's only one set of tensions. Now, okay, so look at this, and then you have force equality, Fg1. Fg, you do have to label 1 and 2 because they're not the same value depending on the mass, right? Now, look at this. Some people, I mean, eventually you'll have to, can look at this and tell me who is winning and who is dead and what is remaining and what cancels out. Now, but sometimes it's not as easy to see it when the forces are bent in different direction. So you can look at the pulley as something that just changes the direction of the force. So when you put a pulley there, the force doesn't change, the direction of the force changes. So sometimes people like to unfold the rope like so. Just imagine that taking these two mass and kind of just like unfolding them, flattening them on the table. So then what it looks like is something like this. So M2 is going to have Fg2 and M1 is going to have Fg1. So just unfolding it. And then where are the tensions? If you draw it this way, then the tension will be this way, right? So tension and tension. Okay. Now, this unfolding method is not necessary though. It's not. I mean, a lot of the time people can do this without unfolding it, but if that helps you, right? Okay, moving on to the next page when we actually put some numbers in this. Okay, so we have two masses. Oh, now this time with numbers. Oh, they're exactly the same mass as before, the 60 and 30, 6 kilogram and 10 kilogram. So let's free body diagram this first. So we have two Fg. I'm going to have to name them 1 and 2. So how about the one on the left is Fg1, the one on the right is Fg2. I know you are able to do force equality Fg equal to mg. So I'm going to skip that. Okay? I'm just going to write down. So 6 kilogram is what? Multiply by 9.8, right? 58.8 Newton. So I'm skipping that calculation. You should not be. 4 kilogram is 39.2 Newton. Okay? Now, I'm skipping that calculation again, because you should know mg at this point. Tension. Let's do it in this color right there. Tension. Tension is the same tension. Okay. Let's do a flattening the graph game. Right here. Right here. Tension. Tension. That's the 6 kilogram. That's the 4 kilogram. So we have Fg1 going this way, Fg1, and we have Fg2 going this way, Fg2. Fg1 is 58.8, Fg2 is 39.2 Newton. Now, on the actual test, you should show me how to get Fg1 and Fg2. Okay, just say Fg1 equal to mg, and then give me that mass, and you don't have to write 9.8. Okay, G is 9.8 for any question that's on Earth. I know that. You don't have to write 9.8. Just do it in your calculator and get me the final result. Okay, look at this picture. Now, if you cannot tell who is winning or who's losing by looking at the pulleys, you should be able to tell by just looking at the flattening pictures, right? This is a tug of war situation again. So, now, step 1. Cancel or kill all the forces that cancels each other out. For example, tension and tension is gone. Now, is Fg1 and Fg2 gone? No, it's not. Fg1 and Fg2, unfortunately, is not the same value, so they are not gone. They are fighting each other. Okay, who is winning? Who wins? Obviously, the stronger force wins. So the winner in this case is Fg1. Okay, so Fg1 is the winner because the tension doesn't really count. Now, if Fg1 is the winner, which way will this system start to move? This way, right? In this like counterclockwise direction. How come? Because the mass on the left hand side is heavier, so it's going to go down first, and the 4 kilogram mass is going to go up. So we need the winner. We also have the loser on the other side. So now let's take a look at this entire picture and write down the F net of the system equation. So F net system. To get acceleration, we have to do system first. Okay, F net system, which remember equals to an equation that can change from question to question. Now in this equation, we are going to do winner minus loser, which is Fg1 minus Fg2. Now you can see Fg2 is literally fighting on the other side. Fg1 is trying to make the whole system goes counterclockwise. Fg2, if you look at the pulley, is trying to make the system go clockwise, right? So Fg1 is trying to make it go this way. Gravity 2 is trying to make the system go this way. So they're actually fighting each other. Even though they're pointing in the same direction, they're exactly fighting each other. Fg1 and Fg2 are enemies, not friends, because of that pulley. So therefore, we know that, well, because the fighting Fg1 is bigger, the value, so we know Fg1 wins. Pick the winner, subtract by the losing side. Okay? Now, what does F net equal to? F net equals to MA, but this is a system, so F net equal to system MA. Fg1 minus Fg2 is just a number, minus another number. So 58.8 minus 39.2, mass of the entire system, which is 6 plus 4 kilogram. So acceleration is the only thing you need to find. Subtract 58 by 30 something, 9, and then divide by 10. The acceleration of the system is now done, which is 1.96 meter per second square. Now, why don't I just say acceleration of the system? Because I don't know which one they want. They said acceleration of the system, right? What is acceleration of individual object? So for example, look at this picture. What is acceleration for the 6 kilogram mass? For the 6 kilogram mass, then it will be 6 kilogram mass go down. That's the direction. But what about the 4 kilogram mass? That one goes up. Yeah. So 4 kilogram mass go up. So either one of these two directions are fine. You do not have to say both. Pick one, whichever one. So that's your final answer. Okay, but you don't have to say both direction. Pick one. Now, guess what we're going to do next? Tension. Of course, tension, right? It's always tension after acceleration. So, when you're solving for acceleration for the whole system, make sure you use total mass. When you're finding tension, you only use one mass. Okay, so now let's go find tension. So, well, actually, in this question, right here, tension. To get tension, we have to pick one box. It doesn't matter which one. Both of those two boxes have exactly two forces on it. So it's exactly the same in terms of difficulty. So pick your favorite one. Okay, now I'm going to pick, because I think last time we picked M1, M2. Why don't I pick like this one this time? Okay, I'm going to pick for the 4 kilogram box. Okay, bear with me. 4 kilogram box. So now you draw the 4 kilogram box. Free body diagram, make sure you have gravity 2 right here. And then we also have tension. Mr. Tension up here. Tension. Okay. Now, then ask yourself, which way does this box go? Well, I will look at right here. Hey, it goes up. All right. Now, draw the acceleration going up for yourself so that it gives you an idea. A reminder. Hey, I'm your acceleration. You just got me 1.96. I'm going up, by the way. Okay, so Now, this little arrow right here, the acceleration, tells you who wins, because an object can only accelerate in the direction with net force. So if the net force is pointing up, then between these two, tension and FG2, who wins? Of course tension wins. Okay? It's whoever that points in the same direction as the acceleration that wins. So winner, winner, chicken dinner is our tension. Okay? So now let's write down a mini net force equation. Now this time is no longer distance, no longer the system net force. This is only for the 4 kilogram mass. Okay? So 4 kilogram mass only. Now, so F flat equals to, well, in this case, what? Winner minus loser. Tension minus Fg2. Okay, so that's the equation you need to write down for only this box. F net equals to MA. So MA, tension. Well, we got tension earlier, right? Oh, no, we don't. We're looking for tension. Okay, cool, leave it. How about Fg2? Oh, we definitely have Fg2 earlier, 39.2. Okay, so that numbers we have 39.2. How about the mass? 4 kilogram. How about the acceleration? Mr. Chow, we don't have acceleration. Oh, yeah. No, we did. We did. In part 1 of your question, we did. Okay, multiply that together. Okay, so 4 times 1.96 is equal to tension minus 39.2. Now, how do you get tension? Add the 39.2 to the other side. Okay, so 4 times 9.6 first, and then add 39.2. So 4 times 1.96, and then you add 39.2. Okay, so tension is now done. Tension, tension. Okay, so this is 58. Now give me 1 second. Let me double check the calculation so that. So this is net force 1.96. So 1.96 multiplied by 4, and then plus 39.2 is 47 Newton. Okay, so 47 Newton, and we are done. Ching, 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 ching. Okay, so 47 Newton. It doesn't matter if you pick the 6 kilogram box. Now, if you want to, like for the sake of practicing, right? If you want to go ahead and do this exact question with the 6 kilogram box, you get 47. So that's why it doesn't matter which one. Just pick one. Ladies and gentlemen, now, I said I give you level 2, and now I give you level 3. A mass on a frictionless table is attached to a hanging mass over a frictionless pulley. Okay, so this is kind of weird. So first of all, I know pulley usually have friction, but the frictions on the pulleys are very, very advanced to calculate. So we will always assume no frictions on the pulley. Now, but we will sometimes have frictions on the table, and that will make the question harder, so we will do it in the next picture. This is only friction on the pulley, no friction on the pulley and on the table. So frictionless pulley, frictionless table. Free body diagram, go. Now, this is what I consider level 3. Level 3. Which one is 1 and 2? Doesn't really matter. I'll say this is FG1 because I draw it first. And that's FG2 right here. I'll put tension up like this. So this wire is bent around. So this is also tension. So these two tensions are internally canceling out each other. Okay, what else is in this picture? What else should be in this picture? I should have normal force up here because that is actually touching on a surface. Now the box 6 kilogram one is hanging on the side. It's not touching a surface. There's no tension, no friction for it. No normal force for it too. Okay, and that's it. I can't draw anything without making some numbers up. Now you look at this and you say, okay, so how are we going to balance this? So this rope is running like this way. Okay, so you have to think about the forces as either going along clockwise with this yellow line or going against, which is counterclockwise, this yellow line. Okay? Now, first, we find out who are destroying each other. Normal force FG2, usual suspect, right? They're dead. If they're not the same, flying cars, remember, submerging human being, that's very scary. Why did I not label FN with an FN2? Some of you are asking that question in your head, I think. Well, we don't have to, because there is only one FN. The other object is not even touching a surface. Tension and tension, usual suspect too. Even though they're pointing in like this weird direction right now, if you straighten out this part so that you make it go like this way, you will see that the tension is going this way to the left, which is completely canceling out that tension to the right. So yeah, no more tension. And you say, well, Mr. Chang, you cut off everything. No, I didn't. I did not cut off everything. I left one. FG1. That's untouched. So win. FG1 is the winner. Okay, so now again, this is a tech lead. That is not necessary. You won't get marked for this, but you know, if you straighten it out, for some people, it's easier to see why FG1 is the only thing remaining. Okay, so I'm going to draw it out and I'm going to cancel. See, FN, FG2 gone, tension, tension gone. Look, the only force left is here. FG1, right? You can't have FG1 fighting anything else because there is nothing else that we wrote down, that we are allowed to write down. So 8 kilogram, 6 kilogram, FG1 is the only one remaining. So, so it's not a pi force anymore. So in this net force on the system, we have FG1. That's it. And F net equals to MA. So the only difference is, should I call it mass total or system? I'll say system. You can call it mass total if you want. Right? Like that. So what's FG1? We actually did not calculate FG1, but that's okay. It's 6 kilogram, whatever, right? So M1 times force of gravity, where M1 is 6 kilogram. You know, numbers. What about the mass of the system? Well, that's 6 kilogram plus 8 kilogram. Okay, so that's different. And then the acceleration. So what we are trying to find is the acceleration. So get the number on the left, which is 6 times 9.8. Get the number on the right, 6 plus 8. So 50, oh God, that's not the pencil I want. 58.8 equals to 14 times the acceleration. So divide both sides by 14. Dun, 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 dun. Dun, 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 dun. 4.2 meter per second square. If you give me this answer, you get 4 out of 5. Because you forgot to tell me the direction. 8 kilogram, right hand side. Or 6 kilogram, downward. These two objects are actually moving a different direction. If you look at the 8 kilogram box, it's moving to the right. If you look at FG1, because it's winning, it's sliding down, right? This system, entire system, is going in this direction. So it depends on which box you're looking at. The direction is going to be different. It's the same number, 4.2 meter per second square. But the direction, now if you use the 8 kilogram box, it will say 8 kilogram box is going to the right. If you have more than one object that's 8 kilogram, then just tell me which one, the one on the top, right? Just write it down. Usually they won't, I mean, you know, why not? Why? Usually different mass, right? But turned out to be the same for some reason. There we go. All right, moving on. Tension. Of course, we're finding tension. So you're starting to see a pattern, isn't it? F net, tension. F net to get acceleration and then tension. Pick one box. I hope you're saying FG1 because mass 1 has 2 forces, mass 2 has 3. Redraw mass 1. Free body diagram it well. FG1 tension. Okay? Now, 6 kilogram. All right? We have to determine who is the winner. You cannot just make up a number. Look at the direction of your acceleration. 8 kilogram go to the right. That means the 6 kilogram go down. This is the acceleration, which is worth 4.2. There you go. So, who wins in this tug of war? Whoever acceleration points at wins. So, the last question that we did, it was tension who won. This time, it's Fg1 who wins. And there is also a losing side, which is tension. It's pointing in the opposite direction, so you also have to include that. So Flat for the 6 kilogram box only is equal to Fg1 minus tension. Flat is MA. Fg1 minus tension. Fg1 is 58.8 minus tension. So we don't have tension. Remember, tension is what we're trying to find. Well, what is MA? Well, MA is obviously 6 kilogram multiplied by the 4.2. So 6 times 4.2. Okay, so 6 times 4.2, 25.2. All right. Now, let me do this one in a bit more detail than usual. So how do you get to this tension? I would move that to here and swap it with the 25.2. So in my head, it becomes tension equal to 58 minus 25. So 58.8 minus that. Tension is done. Okay, so tension is about 33.6 Newton. Done. Okay, now level 3. We are killing this. Good. There's going to be so many questions once you try the practice. You know, I can just add more stuff to this, right? Like that. And add another pulley, like that. What if you get this question on the test? They're actually not as difficult as you think. They're tedious if you add more stuff to it. But, let's deal with 2. Now, this time, the only difference is there's a friction force of 25 Newton. In your practice question, you have questions like that, but they won't even give you the friction force. So please find out Fg, Fn, and find your own friction force first. They said the table has friction. The pulley is still frictionless. We will see pulley frictionless for every question, so just don't even think about it. Force of gravity, let's go. I'm still going to call the one that is hanging Fg1. That's my habit, but you don't have to. It's a name. You can call him, like, Tension Tommy or whatever. Like, it's a name. It's a name. Tension. So tension doesn't have to have the name right now. Just call tension because there's no other tensions. If you have more than one wire, there would be. Normal force, which is the same as Fg2. Now we have to determine which way to give our friction. So let me give you options. Now, first of all, where is friction? Is friction on this box or friction on this box? On the vertical box right here, friction, if there is any, is only air resistant, which is too small, we don't count for physics 11. So friction should be on this force because this box is the only one that's actually rubbing against the surface of something. The other box is hanging in the air. It's not rubbing against anything. So friction is on 8 kilogram box. But should I draw friction this way or to the right hand side? Which way should the friction be on the box? Well, to answer that question, you have to first ask yourself, which way is the system moving if there's no friction? If there's no friction, the system go this way, right? You might say, Mr. Shang, wait. But the 6 kilogram block is a lot lighter than the 8 kilogram one. Wouldn't it not be able to move it at all? Without friction, it will always move it, no matter how small that 6 kilogram box seems. Without friction, no one is fighting Fg1. No one is. Look at the last question. Who is fighting Fg1? Tell me. Who is fighting Fg1? No one. No one. So what does that really mean? What does that really mean? I can have a double-decker bus in here, attached to an apple. And If there's no frictions on the ground, let's say it's a double-decker bus with ice wheel on a ice road. Okay, that's like as little amount of friction as I can imagine in our everyday life, except for going into space where we can like eliminate all the frictions when the object's not touching a surface, right? Like even that is going to move. Like you can put like an apple on there and it will move a double-decker bus. Okay, if there's no friction, it is ridiculous. Now, luckily, you think this is ridiculous because there's always friction. Okay, thank God for that, right? So there is friction. So if there is friction, then which way would friction point? Now, you should already guess that by this point because I said the system goes this way, right? Friction is always opposite to the direction that you want it to go, which for the 8 kilogram box is the right-hand side. So therefore, friction points to the left-hand side. Okay? So here is the free body diagram now in completion. Okay? Ladies and gentlemen, let's play the game of who is left. Every time we play that game, Fn, Fg2, gone. Tension, the other tension, gone. So what is left? Don't cross out Fg1 and friction. You don't know if they are the same. You don't know. Tension is always the same internally. Normal force and gravity in this case is the same. But you don't know if Fg1 and frictions are the same. So there are 3 scenarios, just like before when we learned about frictions during yesterday's class. There are 3 scenarios. Either this applied force, kind of like applied force in here, is bigger than friction, then system accelerate this way. If applied force is equal to friction, then you can have 2 situations. Either stationary, stay there, nothing move, or constant speed, low acceleration, sliding down. Now remember, this system will never slide up. Have you ever seen something hanging like this and it's sliding up? I mean, that's really scary. Okay, it won't. Friction cannot initiate motion. Friction can erase motion, can make it slow down, but not initiate motion. Okay? So, scenario 3, friction is much bigger than Fg1. So friction is a giant force. Fg1 is a small force. Then what? No one move. Stay there. That's it. 3 scenarios. So let's find out Fg1 and friction and see who is actually winning the game. Fg1 is easy though. I mean, I don't even want to calculate it. Do you want to calculate it? You calculate it. It's 6 kilogram, 9.8, you know. It's 58.8. Now, I'm allowed to do this. Skip this step, Fg equal to mg, because I'm Mr. Chang. You're not allowed to do that. Okay? I have done this thousands of times. I've been teaching physics for like more than 10 years. So I have a little bit of, leverage, right? Okay, so friction. Now, in this question, they're nice. In one of your or multiple one of your assignment questions and your homework questions and your eventual test questions or your lab project questions, friction force will not be given. So what you need to do, find Fg2, make it equal to Fn, and use mu to get you friction. Like go that way. Okay, then you get friction. All right, so in most questions, you have to find your own friction. So number 1, get Fg2. Number 2, make it equal to normal force. Number 3, do mu Fn. Go like that. And then you can get your friction. Now, in this practice example, friction is given, 25 Newton. But seriously, I will never give it to you. I will almost never give it to you. So for a practice question, yeah, sure. Okay? Now, this is a game between who and who? Friction and Fg1. That's it. It's a tug of war fighting for dominance between a clockwise force and a counterclockwise force. The system either go this way or it doesn't go at all. So what is the result? What is the verdict? Move, right? The verdict is move because 58.8 Newton is greater than 25 Newton. So the system can and will move. So for the box on top, 8 kilogram, slide to the right, accelerate. For the box 6 kilogram hanging on the side, accelerate downward. That's what's going to happen. So let's circle the winner and write down our net force equation. As you can see, most of your work is done on the free body diagram. You see that? Like most of your work is like here, right here. This is work. If you're missing that diagram, you get no work. In my point of view. Okay, this diagram shows me all the physics. Now, and then we do a little bit of math, like 1-2 line. Okay, let's go for it. So if you miss that diagram, you're getting like 2 out of 5. No matter what you do for the rest of the question. Flat auto system, because there's more than one object. This case, who is winning? Fg1. Who is losing? Friction. Fg1 minus friction. Oh, by the way, how come I don't have to label friction as friction 2? Did you see a friction 1? Right, I don't have to label friction 2 because there is no friction 1. If you have 2 boxes and they're both having frictions on the ground, then you will have friction 1 and friction 2. They will actually be different numbers, so you have to worry about that. Take note. But only one object, of course, it's okay. Okay, F flat, in this case, is equal to Fg1 minus Fg2. And now we're going to write down our system net force, which is equal to system mass times acceleration equal to Fg1 minus friction. Okay, so now the Fg1 is 58.8. Sometimes I forget. Friction is 25. So let that side subtract. On the other side, we have 8 kilogram plus 6 kilogram, which is the mass of the entire system. Multiply by that, subtract this side, which is 23. No, it's not. Sorry, 33. 33.8. Okay, now I will use the calculator because I can't divide by like 12 on this thing. Okay, so using a calculator, divide that by 14, 2.41, 2.4, 2.41. You know what? We lead the answer for the next part of the question, so let's go 2.41 with an extra bit of accuracy. I mean, if I'm only presenting this acceleration and nothing else, obviously I won't care. I do not care about what that number is. Like, I will just round it to 2.4 and call it a day. But I lead this number like immediately after. So extra accuracy is 1. Okay, I did this question, and is something screaming in your head yet? Mr. Chang, you forgot the direction. Yay. Please remember direction. So you can pick either one of the object. Let's put down 4. So you say down 4. 6 kilogram box. How about that? That's a good direction. Okay. Oh, I have to officially report to all of you that my screen is now jumping. Like I'm looking at a screen that's like a screen on my tablet that's actually jumping around at this point. So, okay, you know what? We're gonna pick the 6 kilogram box also, because why not? For our tension. So this is the last thing. Fg1 tension, and then we draw the direction of the movement, which is what? Which way does it go? Down, right? We say go down, down, down. For what? This is 2.414. That's the acceleration. Now, so if the acceleration goes down, then which force win? Well, Fg1 win, because Fg1 is the one that goes down. So set up your net force for the box only. Take the winning force minus the losing one, and then make it equal to Ma equals to Fg1 minus tension. Mass 6 kilogram. Acceleration 2.414. Fg1 58.8. This screen is jumping so much, it is very scary. And subtract by tension. If you missed Friday's class, you have no idea what I'm talking about. I saw everyone like the jumping of my screen. My tablet overheats after an hour, and it affects its display, and the display jumps like like it's shaking, like the entire display is shaking on the screen. Okay, so now look for tension. So what do? Swap like this, right? And then subtract, done. So that's why I'm trying to finish this up. 44 Newton. There. Okay, jumping 44 Newton. Okay, so that's it. Now, you are probably going to have a lot of questions with the exercise, which is what I want. Okay, I want you to try. I want you to actually try them. If you can do these questions, the rest of the chapter, the entire chapter, everything that we have learned, Newton's law, how to do net force equation, how to draw free body diagram, how to find friction, tension, except for spring, which is not in one of these questions. Everything that we have learned is in one of these questions, right? Think about it. Everything, except for the gravity in space equation. So if you can do this type of question, then most of what we have in this chapter, you're ready for it. Okay? So worksheet, I think is called like 4.5 or worksheet 5 or 5.5. I'll find out the name. Okay? And that's it. Goodbye. Pausing.